Let's see. Yeah, I did. I rebooted the computer and did a number of things, but it's still really quite slow. All right, so I have this, and so if you plug in your experimental, I just set up a formula to calculate the, actually, I don't know if you can see this. Am I sharing this? All right, Don, this is what you're looking for. It's just this. So if you type in, let's say for zinc chloride, you had 6.7. Oh, I gotta enable editing. I do have some hard drive errors that wasn't able to repair. And so that could be it as well. But this Excel's totally hung up. Let me just quit out of that. Oh, there it goes. Okay. Screen sharing has stopped. His sharing window is closed. Try this. You share. Okay, you uploaded it to Outlook. That's fine. So if you want, it would be nice if you could plug in your pH values here and then email. Then I can compile a list. I was going to do that, getting the data off people's labs, but it'll just take a long time. So that would be great. And so we could plug in some values here, and then I can get the percent errors, and then I'll just share those with the class, what people got. It'll be interesting to see what people got for their errors. So I just plugged in an equation for the percent error. That's it. But also you want to check your pHs here to make sure that you calculated similar pHs or the same pHs. There's another way you can check your pHs. You could just check it, by, let's say, for example, the zinc. Get the zinc calculation here. We can just check. So for zinc, I calculated a pH of 5.0. I could double check it by getting the equilibrium concentrations, which are in magenta here. Oops. This one here and this one here, and then the hydronium, and then plugging it back into K. So when I do that and calculate K, it comes out to 1.00 times 10⁻⁹, which is good. And so that's my check on this. This is the check for the simplifying assumption here. Maybe I'll upload it onto Canvas. That would be better. So I'll make a Canvas thing. And so people can do that, and then I can see, compile a list of this. Then we'll look at the data, look at the average pHs that people got. And so I'll make an announcement on Canvas regarding this. I just don't know how many people have Excel and how many people don't. We do need Excel to work with the pH titration data. So I was going to put out a poll to see Yeah, El Camino, but okay, so El Camino gives everybody access to Excel. Okay, then that's fine. Then we can do Excel, and then we'll be able to work up our titration data. I was worried about people not having Excel. Also, there's been talk at El Camino about people not having computers too, but nobody is thanks. Nobody has come up and mentioned that to me. Yeah. All right, so Don, there you go. There's a good link for you, I think, for getting Office. Yeah. All right, did I miss any questions other than the homework? All right, let me make sure the recording is still on. Yeah. Okay, let's take a look at the homework problems that you asked about. And so I'm not going to bring those out because it's going to take time. 97 and 101. So let me take a look at 97 and 101 in the book I have here. I'll just read out the problems. Chapter 16. 97. Okay, 97. Use the concept of hybrid orbitals to describe the bonding in strong acids given in exercise 78. Okay, so going back to exercise 78 here. The following very strong acids are formed by the reactions indicated here. And so let me do this on the whiteboard. And so they take hydrogen fluoride or hydrofluoric acid, depends on what you want to call it, and antimony pentafluoride, And then, all right, this was hanging out here. This is going to produce this, HSBF6. So how would we name this? You know, the nomenclature like this is easy, it's binary, but this isn't so easy. And so this is an acid. This is going to go by a different name, hexafluoroantimonic acid. Okay, hexafluoroantimonic acid is a superacid. Superacids are, you know, they're acids that are very strong, stronger than, let's say, what's the strongest acid on our chart? HI. Well, HI isn't strong compared to superacids. These superacids are so strong, they can easily pluck protons. I mean, not pluck protons. They can easily react with extremely weak. We have superacids and superbases. Superbases can pluck protons off things like alcohols and that kind of thing. Superacids are very reactive and do those things. So the concept of hybrid orbitals, well, hybrid orbitals we can deal with here. And so this is going to be SBF6. Lewis structures like this are okay for non-complexes, you know, although we call this hexafluoroantimonic acid. So we have something like this. When we look at the orbitals on this, what are they? Now, it depends on how we describe the bonding to the hydrogen. And so think about that. So is this, and then where does the hydrogen go on this particular structure? And so those are questions we need to answer. And so what we probably should do is we probably should take a look at where this comes from. And so where this comes from here is we have HF, this. And then we have antimony pentafluoride. Yeah. Antimony is in the same group as like phosphorus, arsenic, antimony. So antimony has 5 valence electrons here. It would have 5 valence electrons. Now, if we come up with something like this, what's going on with this here, you know, and how are we getting the reaction here? It looks like we're attaching another fluorine to antimony, right? And then what's happening with the H plus? And so there are different ways we could describe the bonding in this particular compound, because here do we have the right number of electrons? So if we take a look at antimony, antimony would have 6 electrons in this particular case, but antimony only has 5 electrons, you know, because antimony, fluorine is going to have 7 valence, antimony is 5, so this structure looks good, antimony pentafluoride. This structure looks good here. But what's going on with this structure, because our electron count is off, unless this thing has a negative charge. If this thing has a negative charge, then we're okay. And the negative charge would have to be on antimony here. And if that's the case, then where did that extra electron come from? Okay. The extra electron came from hydrogen. Hydrogen must have lost that electron. So fluorine took that electron, and then fluorine ends up binding here. And so this is one way of describing this. You know, this would be purely ionic here. This hydrogen being attached to this. This would be the anion here in this particular case. And so antimony has 5 electrons. Fluorine, we have 6 fluorines. Each fluorine is 7, so 6 times 7 is what, 42 electrons. And then the -1 charge, which would be 1 electron here. And so this would give 48 electrons. So this 8 times 6 is 48. Is that right? Yeah. And then we have the H plus here. So this is one way of describing this. If that's the case, then this would be sp3d2 hybridized. And this would be sp3 hybridized here. But in Chem 4, I mean not Chem 4, but in Chem 1A, there are 2 ways of dealing with this. You know, we could hybridize this with the d orbitals in here, or we might not. There's a little footnote in Chem 1A in the book that says that calculations and I think some experimental data showing there's very little dehybridization in there. And so another way of writing this structure, an alternate way of writing this structure, this is Chem 1A stuff, is we don't expand the octet. So what happens is antimony maintains an octet here. Like that. Antimony maintains an octet, and then that, that final fluorine is ionically bound. So antimony should have 5 electrons. In this case, it only comes up with 4 electrons, so it's 1 electron short. Its formal charge is going to be positive. Formal charge on this is going to be negative. And so another way of describing this is by not expanding the octet and hybridizing it with the d orbital, but instead keeping it a hybrid of just s and p orbitals, and then having it ionically bound. This would be a distorted tetrahedral type arrangement here to make room for this ionically bonded fluoride. We could do the same thing here. You know, if we did the same thing here, the antimony would maintain an octet. So we wouldn't have to incorporate d orbital. And so there'd be no d orbital contribution here. And then what we'd end up with is we'd end up with 2 fluorides here. Well, 2 fluorides here is going to get a net negative charge because the antimonies come up short. This is negative, and then we're going to have a hydrogen here. That's also going to be ionically bonded to this whole thing. The ionic bonding with this is going to be strong. So the particular question is, use the concept of hybrid orbitals to describe the bonding in the strong acids given in exercise 78. So this is coming back to the earlier question. The earlier question is regarding, let me see in the chat here. The earlier question is, okay, this is an example where, okay, this is a question from chapter 16, but this question from chapter 16 requires you to go back and look at the material in chapter 11. So on a normal exam, I wouldn't ask you to do something like that on a normal test, you know, necessarily, unless it's something I talked about directly. But on homework, it's fine. You should be able to go back and look. And then on the take-home exam, it should be fine as well. You should be able to go back and look, although I'm not sure I'd do something like this. But use the concept of hybrid orbitals to describe the bonding in the strong acids given in exercise 78. So, so that's one way, but you know, this question is loaded because the concept of hybrid orbitals, when we have an expanded octet like this, is, let me see what page that is on so I can just show you, is also another question, and it's not so clear cut what people fun about this. Let's see if it's in your book. I don't remember what page. But, maybe it was in chapter 10. Let's just see. Well, anyway, if you come up with something like this, that's okay. I'm not sure if you guys even talked about this in Chem 1A. Well, I would have accepted either, you know. Something like this with an expanded octet, so this would be sp3d2, something like that, and then the hydrogens ionically bonded, or having 2 fluorides ionically bound and then a hydrogen ionically bound to this whole thing, which would be an ion, something like that. Okay. And so in that case, this would be, you know, 3 single bonds, no lone pairs, so sp3, but it would be distorted. And then this would be 1, 2, 3, 4, 5, 6, sp3d2, something like that. And so it's just to get you thinking about this kind of stuff, you know. Really what we should be using is we should be using MO theory rather than, well, MO theory, we're going to have these hybrid orbitals, but these are hybridized atomic orbitals. What we should be looking at is the atomic orbitals for this. For the atomic orbitals, we probably don't have to come up, I mean, for the molecular orbitals, we probably don't have to come up with a scheme like this, where we have partial covalent bonding and partial ionic bonding in this. Okay. But it's a question just to get you thinking about that kind of stuff. And then I was looking for the expanded octets. I forgot, it's in chapter 10 or chapter 11. It's somewhere in there. And you can look at that up there. Okay. We'll just move on because this is not so crucial, I mean, for this particular test. Okay, the other question is 101, chapter 16. It's just so you don't forget. You know, some questions like that are thrown in there so you don't forget earlier material. And we've been talking about hybrid. I wanted you guys to review all the hybridization, all that kind of stuff from valence bond theory. Hybrid orbitals are used in MO theory as well. We can take hybridized orbitals like this and do LCAO of hybrid orbitals to come up with the molecular orbitals, the bonding molecular orbital and the anti-bonding molecular orbital. But in something like this, the way I'd visualize this using hybrid orbitals is this is an sp3d. This is an sp3, so we have an sp3d, sp3 sigma bond, that kind of thing. Okay, chapter 16, number 101. In this problem, we will use material balance and charge balance concepts. Pages 761 through 762 to calculate the equilibrium concentrations in an extremely dilute solution of a strong acid, 1 × 10⁻⁷ molar HCl. Write down the material balance equation for 1.0 × 10⁻⁷ molar HCl, assuming that HCl ionizes completely into an aqueous solution. Okay. And so material balance is just atom balance. You know, if we want to balance out the atoms, let's see, is this okay for this? Probably not the greatest, but you know, something we do. And so 101, when we do equilibrium, we've been doing it the way we've been doing it, but there's also something, these concepts of mass balance and charge balance. And so basically, whenever we balance any kind of chemical equation, we have to make sure that the mass is balanced and the charge is balanced here. And so we could have something like this, you know, where we have oxalate reacting with water to produce hydrogen oxalate and hydroxide. And so the mass balance would be the atoms. You know, we got 2 carbon atoms, 2 carbon atoms. 4 + 1 is 5 oxygens, 5 oxygens, 2 hydrogens, 2 hydrogens. So the mass is balanced. And then the charge balance comes from looking at the total charge, you know, -2, -1 here. And so mass balance for HF, you know, as far as an equation goes, is just making sure that all the atoms are accounted for, you know. And so H+ plus fluoride, that would be mass balanced here. You know, HF plus H2O, that would be mass balanced as well. And so we do something like that for HCl. We can write down the mass balance and then write down the charge balance equation, electrical neutrality. And so electrical neutrality, we want the total positive and the total negative. And then use the material balance and the charge balance equations and the ion product for water to show that. Okay, and so this is just different ways of manipulating things mathematically. And one example that you can use to see how you would approach it using mass balance and charge balance, and you just get a slightly different set of equations, is if we go back and look at this. This is something I posted on Piazza a while back. Let me see if I can bring that up here. This one, the pKa of water. So click on that here. The pKa of water. Then basically here's your mass balance, law of mass action. And then we're going to have charge balance equations in here as well. And so we could do it by mass and charge balance. And so this would be an example of solving the equilibria, doing that. And so this one, it's not that you know, on the test, you're going to have to do something like that. You know, I wouldn't necessarily make you do something like that on a in-class test. You know, this would be more like a take-home test, and it would be a take-home test that would be kind of hard. where you would go through and you'd have to figure it out how to do a mass and charge balance, 761 through 762. So you flip back in the book and look at how they describe mass balance and charge balance for simultaneous reactions, especially in sequence. And when you look at their mass balance here, actually, well, I probably should show it to you. Otherwise, it's hard to see. So I need to bring it up. There are some things in chapter 18, we're going to be using mass balance and charge balance in chapter 18. And so we're going to be doing these. This is kind of the preliminary preview of this, starting in this chapter, 762. And it's actually pretty easy, you know, conceptually here. And so let's look at their mass balance equation here. So this is 0.10 molar is 0.10 molar H3PO4. But we know if the beaker is labeled, and this is why I did it like this, if the beaker is labeled 0.10 molar H3PO4, is that all I have in there? Is 0.10 molar H3PO4? The answer is no. I have to look at the total inventory that I have in there. And I talked about this when I was doing the H3PO4. This was a pretty good example for that. What I talked about is this: we have an inventory. It's not going to be all H3PO4. Some of this H3PO4 will remain because it's a weak acid. And so I have some there. We calculated it for 3 molar. But some of this will hydrolyze into dihydrogen phosphate. And some of this will hydrolyze into monohydrogen phosphate. And some of this will hydrolyze into phosphate here. And so it turns out that I don't just have H3PO4, I have these 4 species. And if I'm looking at an initial concentration of 0.1 molar, then that means I have 0.1 moles of this per liter, which means I have 0.1 moles of phosphorus atoms per liter. And those phosphorus atoms cannot disappear. Those phosphorus atoms have to stay there. And so what that means is that the combined concentration of all these, you know, let's say out of this, I'll call it 0.100 because it's easier. Let's say out of this 0.100, I'll call it 100%. 67% of the phosphorus atoms end up here. Well, what happened to the remaining 33%? Well, the remaining 33% of phosphorus atoms are distributed between these 3 species here. And so all 4 species contribute to make 100%. And so the percent of the phosphorus atoms that end up here, we'll call percent in here. The percentage of phosphorus atoms that end up here, here, and here. This combined total has to add up to 100%. And so that's easy, that's simple enough, right? The phosphorus atoms can't disappear. So if I had 100 phosphorus atoms and 67 of those end up here, then the remaining 33 have to end up in these species here. That's mass balance. That's a restriction. And so I don't know if you remember this, but I proposed doing phosphoric acid using the combined method. Does anybody remember the combined method? I proposed using the combined method. That is, in order to figure out the speciation here, we had to do Ka1, Ka2, Ka3, and Kw. Kw is not going to give us the phosphorus, but Kw will give us the other species present, which is important because there's hydronium. In hydronium, we can't violate the law of mass action there too. The law of mass action is atoms magically appear or atoms magically disappear. In the combined method, what I did was I just said, okay, what I'm going to do is I'm going to combine Ka1 times Ka2 times Ka3. That is, I'm going to add up Ka1, Ka2, and Ka3 to make one equation, which I called Knet. Knet, the reason why the combined method fails, and I didn't call it this at the time, I explained it a different way. The reason why the combined method fails is because it violates the law of mass action. The combined method fails because it's a violation of the law of mass action. And what I said during the time is this: I didn't say it's a violation of the law of mass action, but maybe I should have. What I said was, the combined method assumes all the phosphorus ends up into two species. Go back in your notes. The two species that all the phosphorus ends up in is phosphoric acid and phosphate. But we know that the concentration of phosphate is extremely small. And most of the phosphorus ends up in phosphoric acid, and a lot ends up in dihydrogen, and a little less ends up in monohydrogen. And so what happens when we use the combined method for phosphoric acid is we lose these two species, because those cancel out when we combine the equations. Those are intermediate species. And since those two species disappear, and we know those two species are significant, then the combined method fails, because these two species are automatically eliminated in the law of mass action, what we would generate for this particular equation. But I didn't want to get into it at that point in this context, because we're going to talk about it later, but it's the same kind of deal here. You know, the combined method fails because the combined method eliminates this and eliminates this, and then puts all the phosphorus into this species and all the phosphorus into this species, which is incorrect. All right. Likewise, the charge, you know, when we look at the total charge, the total charge has to balance out. That is, the total positive charge has to equal the total negative charge. And the total negative charge is going to be generated by 4 species. So if we eliminate Kw, let's say, you know, then we're assuming this is very small, let's say. Or if we eliminate, well, if we do the combined method, we're eliminating these 2 species here, this one and this one. Then if we use the combined method, then it doesn't quite work out. And so what we're not going to do is we're not going to make any assumptions. We're just going to go through and do the whole thing. And so the total phosphorus is going to end up in 4 species. 1, 2, 3, 4. The total charge is going to end up in, well, the total positive charge is going to end up equaling the total negative charge. That's it. And then what we can do is we can use these restrictions to solve a system of equations. So basically, with 4 equilibrium constant expressions, a material balance equation and a charge balance equation, we have 6 equations involving 6 unknowns. In principle, this system of equations can be solved to find the 6 unknown concentrations, either by making appropriate simplifying approximations or by computerized calculation. The method outlined here, I got to go back. The method outlined here is ideal for computerized calculation. Okay. And so we're going to solve a system of equations here. to be able to solve that. And so we go back to the problem number 101. Actually, let me see what page that was on. That was page on 787. There's another reason I signed this problem. The other reason I signed this problem is because this is how Visual Mintech does their calculation. Visual Mintech is this computer program, and Visual Mintech is going to solve the simultaneous equilibria using mass and charge balance. We're going to do Visual Mintech lab. I think we're still going to do a Visual Mintech lab, except I'm going to have to, for those of you on the Macintosh, I'm going to just have to do it on my computer, and then you'll just watch the calculation. I was searching, and some people are using Windows emulators for Visual Mintech on the Macintosh, but from what I read online, they weren't very successful. And then I don't think anybody wants to put a Windows emulator on their Macintosh anyway. Although I used to have a Macintosh too, and I had a Windows emulator, which was so I could do some other stuff as well. But okay, write down the material balance equation for this. So the material balance equation is just that. Okay, this is the total molarity, and the total molarity is going to be split up into species. And if this species ionizes completely, then the material balance equation is pretty simple. You know, it's going to end up giving you the molarity. So the total molarity of the hydrogen, well, hydrogen only ends up in one species, H+. And the total molarity of chloride only ends up in one species, Cl-. Write down the charge balance equation, electrical neutrality. And so, let's see. And so there's different ways we could do it. You know, very simply, this is balanced here. And so the 1 times 1.0 times 10 to the minus 7 molar for HCl. Well, HCl ends up into two species. The 1.70 times 10 to the 7 molar is going to end up in these two species here. And so this one will be 1.0 times 7 minus 7. This one will be, so we could write this a little equivalent expression for that. Write down the charge balance. Well, the total positive charge is equal to the total negative charge. You know, we got to change the sign. This total. And so this is just the molarities here. And since there are multiple, if we had multiple species, it'd be more complicated. Use the material balance and the charge balance equation, the ion product for water, to show that the hydronium squared minus C naught would be the initial concentration, which is here, times the hydronium ion concentration minus Kw is equal to 0. So show that mathematically. Use the quadratic formula to solve the equation for hydronium, calculate the hydroxide, compare this value for chloride. What conclusion can you draw from this comparison? And so this is just a different way of solving it. And so, so it'd be challenging. It's just, since we didn't do it this way, we haven't been doing it this way, it seems quite complicated, but it's not that bad. Unless you, of course, you get 6 equations and 6 unknowns, then it becomes a big headache. All right, so the purpose of assigning this particular problem wasn't to make you master this. It's to, okay, this is the next step. After you get familiar, well, there's a different way of solving these. And then we're going to be looking at it in lab. And that was with Visual MinTech Lab. Okay. The other thing is this is an advanced problem, so the advanced problems obviously are going to be hard. But this one would be good for take home, maybe. We'll see. Okay, other questions? And if I didn't answer any of the questions clearly, just go ahead and restate those or let me know. Or if I missed your question, just let me know. All right. If another question comes up, just post it there on the chat. And take a look. This one would be kind of a long, this one would be great for a take-home exam, but I said I wouldn't make the take-home exam much harder than the usual tests that I give. And so this wouldn't have been a candidate on an in-class exam unless the exam had a lot of time maybe, or, the thing is somebody approaching this new is going to take a lot of time to do it, obviously, because it's not so easy, but if you have experience with this, it'll be a lot easier. All right, what I want to do is to not fall too far behind, and I already spent a lot of time here talking. I want to talk about the titration curve. And the titration curve here, we had this region which we called the excess acid. This is the excess acid. Let's see. So excess acid, and so we don't have enough base to neutralize it. And so what happens is if we have excess acid, some of the base neutralizes the acid and converts it into our basic salt, which we talked about earlier. And so when we have excess acid, in this case, acetic acid, and we have some salt, the sodium hydroxide reacts with this excess acid to produce sodium acetate, which is what we have at the equivalence point. We're going to have a mixture. The mixture is going to be excess acid, acetic acid, and sodium acetate, which is the product. And so this is actually step 2. In step 1, we add the sodium hydroxide. In step 2, we end up with a buffer. In step 2. All right, in this buffer region, there are certain points, and we talked about the initial pH here, and then the pH here a little bit. But in this region, this is the buffer region here. And in this region, in this buffer region, we could use the Henderson-Hasselbalch equation to describe the product buffer that results, the HH equation. Only at the extremes would the HH equation fail. And so the HH equation we'll use over almost the entire range, but as we get closer to the equivalence point here, then the amount of excess acid is minuscule. If the amount of excess acid is minuscule, it doesn't really act as a buffer. Or right at the beginning, at this extreme, it's all acid. The amount of conjugate base, that is the amount of product, is minuscule. So the amount of sodium acetate here that we form is minuscule. It's primarily a acetic acid. And so we'd have to use ice at the extremes here, and we wouldn't use the HH equation here. We'd use ice here. But if we can use the HH equation, that means a lot of these calculations are actually very rapid and not too difficult to do. And so I need to write some additional stuff here. And to write some additional stuff, I'm going to just clear this for a second and talk about equivalence points. And so the The equivalence point here, that is once I've neutralized all my acid, so there's no more excess acid. I'm just left with salt and water. The salt is sodium acetate. And I've neutralized all the acid. Well, how much sodium hydroxide did it take to neutralize all of it? 25 milliliters. And so we call this the equivalence point here. I've added 25, I've neutralized all my acid. Well, what if I only add half the required amount? So I'm at 12 and a half. If I only add half the amount, 12 and a half, then this is called the half equivalence point right here. This would be the 1/2 equivalence point. This would be the full equivalence point here, the 1/2 equivalence point. Well, it turns out the 1/2 equivalence point is an easy calculation. And in fact, it's not really a calculation at all. The pH is equals to the pKa. And we're going to show that by calculation at the half equivalence point. But some of these other points are pretty easy as well. At the half equivalence point, the reason why the pH is equal to the pKa at the half equivalence point for any weak acid is like this. And so let me do that over here on the side. If I take any acid, weak acid like acetic acid or whatever else, and I'm adding sodium hydroxide to that, and this is going to form sodium acetate and water, then what happens here is, let's say I start off with a full equivalent. So I have a full equivalent of acid. A full equivalent of acid would be like 25 milliliters. That would be a full equivalent. And so I would just call it 1 for one full equivalent. And I neutralize half of that equivalent. And then I have no sodium acetate, water is pure liquid. Then sodium hydroxide is a strong base. Strong bases react to completion. So I'm going to lose half of my original. And so at the end of this, I'm going to have half an equivalent left of acid. I've neutralized half of it. I have half remaining. The sodium hydroxide is a limiting reagent. And so that goes to 0. And then the half of the acid that was reacted gets converted into this salt. It turns out this salt is the conjugate base. And so at the end of this, I have a half equivalence of acid and a half equivalence of sodium acetate. In other words, a 1-to-1 mixture. If I have a 1-to-1 mixture, and this is in the Henderson-Hasselbalch range, then I can use the pH is equal to the pKa plus the log of the base, in this case the acetate, to the acid ratio here. And so the acetate's 1/2 equivalence, and then the acetic acid is 1/2 equivalence, so that's log of 1. Log of 1 is 0. So this is just equal to the pKa plus 0, or just equal to the pKa. So this happens at the half equivalence point because I've neutralized half of it and I converted it into salt. So the pH is equal to the pKa there. But there's some other very easy calculations that we can do in addition to the half equivalence point here. And so let's take a look at some of these that we're going to consider. In addition to the half equivalence point, some other ones that help in graphing this out quickly are the quarter equivalence points. So we could do the 1/4 equivalence point. So what's 1/4 of 25? 1/4 of 25 is, I think, 6.25. So it's 1/4 of 25 or 1/2 of the half. 1/2 of the half is 1/4. Or we can go to something called the 3/4 equivalence point. And so what is 3/4 of 25? Well, to neutralize all of it requires 25. So 3/4 of that's going to be, I don't like these numbers. This is why I like to keep simple numbers here, but add another 6 1/4, so it'd be 1875. 1875. It depends on what our full equivalence point is. The full equivalence point is 25 here, so 3/4 of 25 should be 1875, and I'll call it the 3/4 equivalence point. This is an easy calculation. The 1/4 equivalence point, 3/4 equivalence point, we can calculate rapidly. There's more that are very easy. Perhaps one of the easiest, in addition to the half equivalence point, to determine is the 10/11 equivalence point. Okay, we're very interested in the 10/11 and the 1/11 equivalence point. And so I can figure out where the 10/11 is. This is around, what is this, 474. So if we go to 574, it'll be about here. Something right about here. Oops, try to make this a straight line. So this is an important point on the titration curve, and this point is called the 10/11 equivalent point. So I've neutralized 10 out of a total of 11 parts, the 10/11 equivalence point. Likewise, down here, let's be about right here, I think. Right about here, we're going to have another equivalence point that's significant. And this equivalence point is going to be called the 1/11 equivalence point. The 1/11. The reason why the 10/11 equivalence point and the 1/11 equivalence point are quite significant is because the calculation is so easy. And so let me tell you what it is here, and then we'll derive it later. But I'll just tell you right now what we've got. So if I'm looking at the 10/11 equivalence point, at the 10/11 equivalence point, the pH is equal to the pKa plus 1. And at the 1/11 equivalence point, the pH is equal to the pKa minus 1. And so I think with these 5 points, you know, the 1/11, the 1/4, the 1/2, the 3/4, the 10/11, we'll have this part mapped out pretty well if we calculate those, and then we can get it. Of course, we can calculate any other points in here. It's not too bad to do. And so what is 10/11 of 25 milliliters? And so, you know, what is the volume here? So this would be 25 milliliters would be the 11/11. And so what is the 10/11? So if we take 25 and divide it into 11 parts, and we take 10 of those, that would be the 10/11, or we just get it this way. If I want to know what the volume is at the 10/11 equivalence point, I'll just take 10/11 of 25 milliliters. And so what is 10/11 of 25? So 10 times 25 is 250 divided by 11. And it comes out to 22.72 milliliters. And so the 10/11 equivalence point is going to come out 22.72 milliliters in this titration, because this titration has an 11/11 of 25. If our 11/11 is 10 milliliters, it's going to be different, you know, but this is 25. And so what is the 1/11? Well, the 1/11 is going to be just one part of this. This is 10 parts of this. So the 1/11 is going to be 2.272 milliliters here. And so at 2.272 milliliters, I'm going to be at the 1/11 equivalence point, and the pH is going to be the pKa minus 1. Well, the pKa given here is 474, so the pH is going to be 374 here. And at the 10/11 equivalence point, well, the pH is going to be 474 plus 1, which is going to be 574, be the pH here. And so these 2 points are easy. Now, these points are a little bit more difficult to deal with because they're not right on. And so let's talk about the 1/4. Let me give you the equation for the 1/4 equivalence point. We're going to derive the equation for all of these to make it easier. And so at the 1/4 equivalence point, the pH is equal to the pKa minus 0.67. I'm only going to 2 decimals, I rounded this. At the 3/4 equivalence point, the pH is equal to the pKa plus 0.67. And so, you know, these are easy to calculate. They're easy to calculate because of the equation. The equations are quite easy for this. So let's take a look at the equations for this, where I got these equations from for these specific points here. And so what we'll probably do is we'll probably start off with the 1/11th equivalence point and just work our way 1/11th, 1/4, 1/2. Or we'll do 1/11th and 10/11ths first. We'll probably start on the outside and work in. Or start on the inside and work out. Okay. That's probably what we'll do. All right, now for a titration problem, I'm going to do it this long way, and then we'll do it the short way after that. And so let's start with the green one here, and then go to the red ones, and then go to the magenta ones here. So this is the way we do it, you know, if we aren't at one of these special points. If we're at one of these special points, you know, and this were like a multiple choice, you'd want to do it rapidly. If this were like a free response, you'd have to show how you did it. Okay, so we're in the buffer region here. And so we're going to look at the half equivalence point first, right here. The half equivalence. And so that's halfway between the start here and the end of this. The end of this is just when we neutralize it. The end of a titration curve doesn't end until we're way past the equivalence point. In Chem 1A titration, you'd stop here. Okay, was there a question? Okay. Okay, so the first thing is we're going to look at a half equivalence point. Which I had as green, I guess. I think I was green. The half equivalence point is going to be this. We have to look at the titration as a whole. The titration was this. We're titrating in the beaker here, 25.0 milliliters of acetic acid. What's the molarity of that acetic acid? Shoot. Take a look at the molarity. 0.100 and 0.100. Good. Green's probably not the best color for this. Let me change the color. So what I'm doing is I am titrating this with sodium hydroxide. And this is also 0.100 molar. And if I want to neutralize half of this here, then the concentrations are equal, 0.100, 0.100. So to neutralize all of it, I need to add 25 milliliters of sodium hydroxide, this concentration. But I'm only going to neutralize half of it. And so at this point, I'm going to say plus 12.5 milliliters of this sodium hydroxide titrant. And so this is the long way. I said there's a shorter way, and we can do it as well. But the first step we got to do is solution dilution. The reason I'm doing solution dilution is because in order to do all the problems on the titration curve, we need to do solution dilution. In the buffer region it only cares about the ratio, unless we're at the extreme. If we're at the extreme, you got to do it. But you know, I'm not going to take the shortcut. We're just going to do it the long way. And so 12.5 plus 25 gives me 37.5 milliliters of mixture. All right, what's in this mixture? And so this is step I. What's in this mixture is, well, we have sodium hydroxide present in the mixture. And sodium hydroxide started at 12.5 milliliters and got diluted to 37.5 milliliters. So the dilution factor is going to be a 12.5 to 37.5 dilution. What was the original molarity? The original molarity is 0.100 molar. And so this is almost like a 1/3 dilution. And so let's go ahead and calculate it. It's going to be 12.5 times 0.1 divided by 37.5. 0.033. It is a 1 to 3 dilution, 0.03. Okay, now what you have to do is you have to be careful about rounding here. This is 3 bar, so the 3's just continue on, molar. Okay, what's the new molarity of acetic acid? When I look at the acetic acid, I'm taking 25 milliliters of acetic acid and diluting it to 37.5 milliliters. And so it's a 25 to 37.5 dilution of 0.100 molar. Okay, so let's go ahead and calculate that. That's going to be 25 divided by 37.5 times 0.1, which gives me 0.0666. The same thing. I'm not going to round. I don't round until the very end. And so what some people do is they'll just go ahead and round this to 0.67, even 0.07, 0.067, 0.07, something like that. We'll carry some extra digits. Okay, after a solution dilution, then I go to step 1. Okay, step 1 is strongest acid. The strongest acid is HHC, plus the strongest base. The strongest base is sodium hydroxide. So we take the strongest acid plus the strongest base and react those together. So when the acetic acid combines with sodium hydroxide, we're going to form sodium acetate and water. Strong base reacts to completion, so K is going to be very, very large. Strong base, weak acid combinations. So it's very, very large. Okay, let's put in the initial molarities. The other option is we could use millimoles, which is fine. Your book uses millimoles. I use molarity for a lot of calculations. And sometimes I'll use millimoles. For buffers, it's probably easier to use millimoles, but we're setting up this. The way I'm setting this up is the same way I'm going to calculate everything on this curve. And so I'm just using one method for all the calculations rather than mixing and matching methods based on shortcuts. So the acetic acid we're in the excess acid region, so we should have more. I'm just going to go 4 digits here, 5 decimal places. And the sodium hydroxide, I'll do the same. I'll just carry this out to 4. And I don't round. I'm not going to round until the very end. I'm not allowed this many sig figs. I'm only allowed 3 sig figs here, so I'm carrying an extra. Sodium acetate 0. Water is pure liquid. So the change is complete. You know, K is very, very large. Limiting reagent, sodium hydroxide. So we're going to lose all of that. Okay, so when I do that subtraction, I'm going to get 0.0333 molar. Over here, I'm going to get 0 molar. And over here, I'm going to get 0.03333 molar. And so when I look at this, the weak acid, acetic acid, and the weak base, sodium acetate, have the same concentration here. Okay, this is an HH buffer. HH buffer, we don't consider KW. We just go to the HH buffer equation. And so in the final step of this, I'm just going to look. I see what I have left over. The strongest acid, acetic acid. The strongest base is sodium acetate. acetic acid and sodium acetate are what I have left over. Since H as buffer, the pH is equal to pKa plus the log of the base, which is acetate over the acid ratio. This is equal to pKa plus the log of the base is sodium acetate or just acetate. So it's the log of 0.03333, and then the acid is acetic acid, 3.03333, and this goes to 1, which log of 1 is 0, which means that the pH is equal to the pKa. The pKa is 4.74. Let's see, let's make sure. Yeah, here, this is odd. You know, the pKa is 4.74, what we expect, but remember in Chem Collective, they used a pKa value of 4.76. Okay, now we're back to 4.74 for acetic acid. All right, so we're at the half equivalence point. Okay, so the next calculation let's do will be, let's go with the 1/4 equivalence point. How about that? And so let me clear this screen. I'll just save that. I think these are accessible, the ones I saved. Okay, so I'm going to be at the 1/4 equivalence point. And so I do the same thing. If I'm going to neutralize 1/4 of my acid is 25.0 milliliters, and I start over. Each problem I start over again of 0.100 molar acetic acid. If I want to neutralize 1/4 of this, then I have to add in, well, this is the same 0.100 molar in terms of concentration, sodium hydroxide. I have to add a 1/4 of 25, which is 12.5. So I'm going to go plus, no, 12.5 is not 1/4. 1/4 of 25 is 6 1/4. And so I'm going to add 6 1/4 milliliters of this in. Okay, so the first step in a titration problem is solution dilution. And so I'm going to end up with 25 plus 6 1/4 is going to give me 31 1/4 milliliters total. And in that 31 1/4 milliliters, I need to calculate the new concentration of sodium hydroxide. The new concentration of sodium hydroxide is going to be the dilution factor. It's a 6 1/4 to 31 1/4 dilution. So 6 1/4 over 31 1/4 dilution. And the original concentration was 0.100 molar. And so the new concentration of sodium hydroxide is going to be 6.25 divided by 31.25 times 0.1. And this comes out to 0.0200. We're allowed 3 sig figs, so carry 1 extra molar. And okay, now let's calculate the concentration of the HAC. The HAC is going to be a 25 to 31 1/4 dilution. So I start off with 25, end up at 31 1/4. And I'm not going to round this, obviously, because if I start rounding here, the numbers are going to come off of 0.100 molar. And so it's going to be 25 divided by 31 1/4 times 0.1. And that gives me 0.0800, and throw in 1 extra digit to avoid round off. But this is the extra digit is 0. It's not going to change anything. And so that's step I. The next step we do is step 1 here. But I think, are we out of time now? 12:40? Let's see, how late do we go? Yeah, all right, 12:40 is what I thought. So we're out of time. If you want to stick around, that's fine. I'm going to stop, though, talking about the 1/4 equivalence point. We'll finish this problem next time, which is next week. But I'll talk about questions you have for the test or lab or homework or whatever else. I mean, we could go through that homework problem in more detail. Go on. Up to you guys. You don't have to upload the Excel sheet today. That's but if you can, that's great. But just make sure you have the other calculations uploaded. You can email me the Excel sheet, that's fine too. Or Gmail, yeah. Are there any other questions? Yeah, Thursday the test is going to be up. If you didn't measure the pH for HCl, it's not a big deal. Just do the calculation. Test will be up Thursday and due Saturday. It'll be due on Saturday. Okay. Welcome. Yeah, it's going to be the same kind of situation as the loss test. I didn't do the pH because I didn't see it during lab. That's fine. They put it in different hoods, you know. So the 6 molar HCl was probably in a different hood. 6 molar HCl is a very common solution, so they probably leave it in one spot for the entire semester. So just leave it blank, you know, if it, where it says experimental pH. If you didn't record it, it's fine, just leave it blank. A lot of people didn't record all the pHs. It's just not a problem. You're not going to lose any points for that. Well, we can take a look at any other problems that you guys want to look at, or we can go back to these problems here if you want as well, you know, and spend a little bit more time talking about it. I think this particular problem here was number 97 was just to remind you of hybrid orbitals. And this problem here, number 101, is just to state that there's another way to solve these simultaneously, you know. All right, well, if there are no other questions, we might just call it a day, and then we'll see you guys tomorrow afternoon for lab. We're going to continue the buffer lab tomorrow, and then I'll post the test after after our discussion of the buffer lab. Okay. All right, well, thanks for attending then. If there's some other questions, post it on Piazza, and then I'll see you guys tomorrow. End this here. Okay, I'll stop the recording.